Hello and welcome back. Good to see you again. Thanks for joining me. In our last video, we were setting the historical stage for Euclid to come on board, talking about what Alexandria was and how it became a thing and so on, and what was going on in the world around it at that time. In this lecture or video, we're going to set the conceptual stage. How mathematicians thought about what they were doing had changed a bit since the last time we talked about that, which was during Pythagoras. So we're going to start with Pythagoras, talk about some problems that came up, and then proceed on from there, how things changed, and then what did Euclid think he was doing when he was doing it, and what did he think about what he was doing. A lot more mathematics in this one. So philosophy and mathematics. Last one was history. This one's a lot of philosophy and mathematics. So let's dive into that. So, as you recall, the Malaysian school was always arguing over what was first, what was primal. Everything is water, everything is air, everything is fire. And Pythagoras gave an answer that was odd even for his contemporaries. Everything was number. And we came up with a couple ways of trying to understand that. And then from Zeno's paradoxes, we saw that that answer was really problematic in describing real-world situations. It seemed that you couldn't actually move around in the world or stuff like that. What we're going to see today is that that answer is, in fact, even problematic for mathematics. To say that everything is number and that number is sort of the foundation for everything in mathematics leads us to some problems as well. So then mathematicians had to sort of grapple with how they were to think about what they were doing and what they were doing it with. So let's take a look here. What was the issue? All right. Now, we're trying to understand what he could mean by everything is number. And one of the explanations we had was that number means points in configuration. So for example, line segments is just a set of points in a linear configuration. Let's take a look at how that can go wrong. Go to whiteboard here. There we go. All right. Now, lines are made up of points. That means, given any two lines, the ratio of their lengths is just going to be the ratio of the number of points. So if this has S points in it and this is D points in it, the ratio is going to be S over D. Now, we might probably simplify that. So if this line here was twice as long as S, then our ratio is 1 to 2. So however many points S and D may have, we could reduce that to 1 to 2. Because D is twice as long as S. Okay, now what if we take a square of side length S? Now I'm going to write this. It's a little hard to see this, but these are going to be small letter S's. And let's do a diagonal here, and that's D. And let's say we want to know what is the ratio of D to S. Now, since everything is number, everything is made up of a finite set of points in a certain configuration. In this case, the configurations are lines. Ultimately, D over S can just be given as the number of points in D and the number of points in S. But that might be a lot of points, so we want to find that in a reduced form. So let's say that capital D to capital S is the reduced form of this above ratio. So for example, if D was 8 and S is 4, then capital D and capital S might be 2 and 1. So the reduced form of that. Let's see if we can use geometry to figure out what capital D to capital S is, or we could write that as capital D over S, that ratio. Let's chop our square in half here, and let's write these sides as these are capital S's and this is capital D. Now, you're probably familiar with the Pythagorean theorem. The Pythagorean theorem had been known for a long time by now by Babylonians and Egyptians. Pythagoras didn't discover it. But what he did was, and this is important, he proved it. Remember, this is by distinction between real mathematics and just calculating stuff, is this whole proof thing. So it's called the Pythagorean theorem because Pythagoras or one of his followers was the first to prove it. And how did they understand it? Well, they understood it as saying the following, is that if we have a right-angled triangle, and since this is half a square, that's a right angle right there, and we construct squares whose edges lie along the sides of these triangles, this square has area S squared. This square has area S squared, because these are squares, S, 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 S. This square here has area D squared. And what the Pythagorean theorem says is the area of the square on the hypotenuse is equal to the sum of the areas of the squares on either side. Or we could write that as D squared. In the case of if our original thing was a square and this S were the same, this becomes d squared equals 2s squared. All right, now what does this tell us about our d and s? First of all, notice this 2 over here. That means this right-hand side here is an even number. And you're just going to have to go with me on this, but you can prove it. It is provable. This is not a gap in the proof. This is not where the sleight of hand magic trick comes in. If d squared is even, that must mean that d is even. So what do we know about this reduced fraction? Well, we were just able to show that, although we may not know what d and s are yet, we know that capital D is even. All right. That means capital D is equal to 2 times some other number, let's say a. By substitution, we can get 2 times a, then what that b is squared is equal to 2 times s squared. Okay. Now we can distribute this exponent to get 4a squared equals 2s squared, and then divide both sides by 2, and we get 2a squared equals s squared. Now what does this say? This 2a squared here is an even number, and since it's equal to the right-hand side, that gets us that s squared is even. But if s squared is even, then, and again, like I said, this step is legit. That means that s must be even. Why is this a problem? Well, we have both d is even and s is even when we assumed that d over s was in reduced form. If d over s is in reduced form, they carry no factor in common. We have 2 divides d and 2 must divide s, so therefore they're not in reduced form. We get a contradiction. They're in reduced form and they're not in reduced form. Okay, we got a contradiction. What went wrong? If you go back over this, every step in the reasoning is correct. So this is a legitimate proof. The problem is our basic assumption. The problem is our basic assumption that the ratio of the lengths of d, well, let's say even little d over little s, can be written as a fraction. But here's the problem. If we go back to the Pythagorean principle that everything is number, so like over here, that everything is number, by which we mean points in configuration. And these line lengths here we're to understand as the ratio of points in them. Then if s is some finite number of points and d is some finite number of points, and their ratio is the ratio of points in each of them, then we should be able to write it as a reduced fraction. Ultimately, this means that d and s cannot be understood as a finite set of points in a linear configuration. We have just by contradiction proven everything is number is not workable in geometry. So not only through Zeno's paradoxes do we see that it's problematic in explaining the real world, how the real world operates, but through this we see that it is problematic in even explaining how mathematics operates. All right, so there we go. Now, the story is that this proof was discovered by Hippasus of Metapontum, who was a Pythagorean, while he was out sailing with other Pythagoreans, and he showed them these results, that this whole everything number is provably not workable, and they got so rattled by it that they threw him overboard and drowned him. At least, you know, nowadays we may complain about publish or perish, but at least nowadays when we say publish or perish, the word perish is metaphorical. So, progress. How did they handle this? What did they do? And the answer came a little later in 368. We've got a new guy, Eudoxus of Cyzicus. And let's take a look at where Eudoxus was from. So here, once again, is our Mediterranean map. And Cyzicus is a city, right? All right. Cyzicus was a city somewhere around here on the western shore of the Black Sea. Once again, outside of Athens, in the borderland regions. All right. Eudoxus started the school there and actually really made his reputation through some good results. And once he made his reputation, he then was said to travel to Athens and study at Plato's Academy. Remember, all of this was going on during Plato and Socrates' time. Now, how did he make his reputation? What did he do to impress people so much? What he did was this. Just like in the Malaysian schools, if you had a problem with the explanation that everything is water, you might fix it by changing what you thought the primal substance was. Everything is air. This explanation of everything is air might fix some of the problems with the explanation that everything was water. If there was a problem with saying everything was air, you came up with a new explanation. Everything was fire. And hopefully that was an even better explanation. But in the world of mathematics, Eudoxus flipped the story. He said instead, everything was geometry. Geometry was fundamental and foundational. And a number isn't necessarily just a whole number, 1, 2, 3, 4, or their ratios. A number was the ratio of the lengths of two line segments. And it just so happens that some of those numbers, like the ratio of the diagonal of a square to its side, couldn't be written as a ratio of whole numbers. So geometry came first, and then algebra and arithmetic followed up on it. Now, how would this change things? How would this make our mathematics look different? Let's take a look here. I'm just going to go to a whole new whiteboard for this. One way this changes mathematics is that if you're going to prove something in algebra, you need to prove it geometrically, because ultimately algebra is geometry, right? So let's take a look at an algebraic relation here. So let's take a look at the relation that A times B plus C equals AB plus AC. Distribution. How can we prove that geometrically? Well, remember, we are understanding of numbers as the ratio of line segments, or just for simplicity's sake, we're going to talk about them as the lengths of line segments, okay? So we'll say that line segment is length A, and it's just some of those lengths might be irrational. And on the base of a rectangle here, we're going to make part of the base B and part of the base C here. And multiplication, so number is understood as line length, and multiplication is understood as the area of rectangles with a base of one number and the height of another number. Now, the length of the side here is B plus C, right? Addition is just putting two line segments next to each other like that. And then the area of this rectangle here is A, the height, times the base, which is B plus C. Now, let's write the same rectangle again over here, A, and then this is B plus C. But instead, let's take a look at it in a different way. Let's draw a line here. And this line length here is also going to be A. The area of this first rectangle is AB. And the area of the second rectangle is AC. And the area of the whole rectangle is AB plus AC. Since these are the same rectangles, then A times B plus C must be the same area as AB plus AC. So we now just proven geometrically an algebraic relation. And this is what geometry comes first does for us. We need to prove algebraic things geometrically. So we start with the geometry as a primal in our starting place, and we proceed from there. And we get the algebra and arithmetic from that. Okay. Now, we usually think of Euclid in terms of his geometry, Euclidean geometry. But in fact, Euclid wrote about all of mathematics as was known up to his time. It just so happened that he started, because of this Eudoxian perspective, he started with geometry first and then built everything up off of that geometry. So as we said, Eudoxus eventually ended up in Athens. Euclid, it is believed, started his studies in Athens, was exposed, I don't know if he met Eudoxus, but at least was exposed to Eudoxus's ideas. When Alexandria was started up as the next big thing, Euclid migrated there, started his work up there, and wrote his elements and so forth. And like I said, his elements were not just the elements of mathematics or elements of geometry. They were the elements of mathematics, all of mathematics, but just started with geometry and then developed it out from there. So that is the intellectual context into which Euclid is arriving. He is writing a treatise which is going to summarize summarize and organize, that's important, all of known mathematics at his time. It just starts foundationally with geometry because of this whole square root of 2 thing, irrationality of the side lengths and so forth. They had to flip the story, and now everything starts with geometry. In our next video, we will look more closely at Euclid's elements, at his axioms, what things he said, what he thought about what he was doing, and ultimately some problems perhaps even he had with one of his axioms, the 5th axiom, and definitely people had since then. Hope to see you then. Thanks for watching.